Welcome to lecture number 18 for ECE476 Advanced Embedded Systems. In this lecture, we're looking at how to control the speed of a DC servo motor. Kind of like this one, a little, about 100 watt DC motor. So if you need a little bit of background work, if you go to Bison Academy, that is bisonacademy.com. This has many of the courses offered in electrical computer engineering at NDSU. In this course, we're looking at using a Raspberry Pi Pico along with Python and a graphics screen. So what we've covered so far is we can write Python program for binary outputs, binary inputs. We can drive analog inputs and outputs using PWM primarily for the output. We can drive DC servo motors. We can use edge interrupts to count edges from an optical encoder, measure the speed and angle of a motor. We can use timer interrupts to measure time. Put that all together and you can control a DC servo motor. In this lecture, we're looking at controlling the speed of a DC motor. Next lecture, we'll look at controlling the angle, say opening and closing a valve. Okay, so that's where we're heading. So getting started, what we're going to be covering in this lecture is controlling the speed of a DC servo motor. Once you have edge interrupts, timer interrupts, you can control the speed of a DC servo motor. So we'll look at how to model the DC motor, how to measure the motor speed using an optical encoder, controlling the speed using a P and a PI compensator. We'll talk more about that later. The motor we're using is a Clifton servo motor, but pretty much everything in here applies to pretty much any generic DC servo motor. A little bit of background on DC servo motors. DC servo motor has a rotor, that's the armature. This is the part that spins. On it, it has half dozen different electromagnets. It's got a commutator, so one of these is energized at any given time, and a permanent magnet on the frame. What happens is when I energize one coil, it produces a magnetic field. It wants to spin and have the northern pole, south pole aligned with the magnet. As it spins, the rotor shifts in the next coil, and it gets energized and wants to spin. So the net result is you get a torque, causes the motor to rotate. When you model a DC servo motor, that kind of shows up in the model. So the armature is actually an electromagnet that's inherently an inductor. So for the armature, I model the coil as a resistor. Again, anytime you have a long strand of wire, you get resistance and inductance. I don't necessarily want these, but that's what you get. Motors and generators are the same thing. If I spin the motor, I produce a voltage, and the voltage is proportional to speed. That's this guy right here. That's the generator. The faster I spin it, the higher the voltage, and the relationship is the torque constant. Motors are also motors, so as I apply current, I get torque. Torque is proportional to the torque constant. Or torque is proportional to current, scaled by the torque constant. Plus the rotor has inertia and friction. So put that all together, that's the model for DC servo motor. If you do some algebra, solve for the left-hand side, the input voltage is the losses across the armature plus the back EMF. The torque is the rotational inertia plus friction times speed. Solve all this, and you get the transfer function from voltage to speed. Now, typically the inductance is very, very small, so you can usually ignore it. If you ignore the inductance, you wind up with a first-order differential equation relating voltage and speed. What that means is if I apply a step change in voltage, the speed ought to do something like this, behave like a first-order differential equation. And the parameters determine that model. So that leads up to the first problem. Suppose I want to come up with a model for DC servo motor. Well, to do that, I need to find 5 parameters. These 5 parameters pretty much define a DC servo motor. 2 of those are actually pretty easy to measure. I can measure the resistance and inductance just using an RLC meter. For the Clifton motor, the resistance measured as 26 ohms, inductance 12 millihenries. I can measure the torque constant. Again, the faster I spin the motor, the higher the back EMF. So I can either spin the motor at a constant speed and measure the voltage, or, since I can't really do that, apply a constant voltage, measure the current, and that tells you the torque constant. So going around this loop, if I apply 13.54 volts, I measure the speed as 102 radians per second. The armature resistance I measured, the inductance I measured, this is steady state, so that doesn't really matter. The voltages have to balance. So I know that kT times omega plus I times R is 13.54. Solve for kT, and I wind up with kT is 0.1067 volts per radian per second. And if you work out the units, that's also 0.1067 newton meters per amp. So that gives me the torque constant to measure friction. What I could do is measure the no-load speed and the current draw and do an energy balance. On the electrical side, the power in is volts times amps. The mechanical side, the power out is torque times speed. And I also have the losses in the armature. If I measure the current, so here I had 97 milliamps, 13.54 volts, and the speed was 102 radians per second, 26 ohms. I have one equation, one unknown, solve for the friction. And I get the friction is 0.000108 newton meters per radian per second. It's small, but that's kind of what you want. You want the motor to basically have zero friction, ideally. It will always have some. I can measure friction. To measure the motor's inertia, that gets a little bit trickier. The motor that I'm using has a flywheel attached. That's pretty much almost all the inertia that you're going to see. So if I just model that flywheel, it has the density of iron times the radius times the thickness gives you 0.1275 kilograms. That's how much my flywheel weighs. From Wikipedia, the rotational inertia of a solid cylinder is 1/2 mr squared, gives you 0.00013 kilogram meter cubed, kilogram meter squared. Put it all together, I can come up with the model for the motor. So add all those terms in here. This is what I should have based upon my measurements. Now, kind of note, this has two terms. I've got a fast pole and a slow pole. The fast pole primarily is the inductor resistor. As I apply voltage, it takes a little bit of time for the current to build up. That's defined by this time constant. The mechanical time constant is the 4. So it's got some inertia. I'll apply torque. It's going to speed up. When you have poles that are that widely separated, you can basically ignore the fast pole, and it doesn't affect the model that much. Kind of what you're doing, I've got two first-order systems cascaded. At DC, this has a gain of 1. The gain is 1 all the way up to about 2,000 radians per second, which is well past the bandwidth of the mechanical part. So ignore this, call that 1. And here's my model. So based upon measurements, that should be the model of the motor. What that tells you is if I apply a voltage, step change in voltage, it should behave like a first-order system. The DC gain should be 7.81, so if I apply a 10-volt input, it should spin at 78 radians per second. And the transient decay is e to the minus 4t. So in MATLAB, I can simulate the step response. Input a system with a pole at -4, numerator 35.4, have time go from 0 to 1 second, step of 0.01, take the step response, plot it, here's what you get. That's what the step response of the motor should look like. Well, I can test that. But in order to test that, I need to measure the motor speed. To do that, the motor has an optical encoder attached to it. Kind of see that part on the end. So there's the encoder. As I rotate the motor, it outputs 2 square waves 90 degrees apart. And for this encoder, it has 250 pulses per rotation, or if I count all edges, A and B, 1,000 counts per rotation. So to measure the motor's angle, what I can do is just count edges. And if I note that I've been going this way in time, on the rising edge on A, B is low. On the falling edge, B is high. So the edges tell you distance, and high or low tell you direction. In Python, I can do that by setting up the 2 pins on the optical encoder. I've connected those to pin 26 and 27. Set those up for rising or falling or both. Here's just a rising edge interrupt. And then I count. This is the interrupts at the edges. Channel 2 tells you direction. This will give me 250 counts per rotation. I can try that. So here's my code. I am measuring the angle of the motor. I've got 2 interrupts running. Let's just try it this way. I just have the single interrupt running for a falling edge. That'll give me 250 counts per rotation. The angle then is 250 counts per rotation. 1 rotation is 2 pi. That's the conversion from counts to angle. If I then run that, the data is seconds, counts, angle, and radians. If I rotate it 1 time, so that's all the way around once, that was 2 pi radians, 250 counts, twice around. 500 counts, 3 times around, 750 counts. And if we go backwards, go back to 0. That's if I just count the falling edges. When I count both edges, falling or rising, I now get 500 counts per rotation. So this will change to 500. Run that puppy. And I'll get 1 rotation is 500 counts, 2 pi, 2 rotations, 1000 counts, 3 rotations, and back. That's if I just do channel A. If I do channel A and channel B, it is 1000 counts per rotation. So here's 1 rotation, 2 rotations, 3 rotations, and going back. Okay, so that was angle. If I want to measure motor speed, there's a couple ways of doing it. What I'm going to do is set up a timer interrupt to interrupt at 20 Hertz, 50 milliseconds. If I then count edges, I know the difference in edges, so this is going to be my N1, this is N2, the number of edges. The difference in edges is the difference in edges divided by time, 1/20th of a second. That'll give me my speed in radians per second. So same code as before. Here I'm just going to use channel A. Gives you 500 counts per rotation. Rising or falling, 500 counts per rotation. My scalar then is to convert counts to angle. It's 2 pi over 500. For speed, 2 pi over 500 times 20, because my sampling rate is 20 Hertz. If I then run this code, what I'm printing is the time, angle, counts, and speed, radians per second. So if I spin it once per second, 1001, 1002, the speed ought to be 2 pi radians per second. And going backwards, about 1 rotation per second, 2 pi radians per second. There's my speed measurement. Okay, so now that I can measure speed, I can take a step response and experimentally find out what the transfer function of the stepper motor is. So to do that, I'm going to have the Pi Pico outputting 2 PWM signals. That'll go into an H bridge and control the voltage out from 0 to 100% forward and reverse. I'm applying 15 volts in. That gives me 13.4 volts out as measured on a voltmeter. That goes to the motor. The optical encoder then comes into the Pi Pico, and with that I can measure speed and angle. In terms of coding, what I'm going to do is, let's do a static test first. I want to see what is the steady state speed versus voltage. That'll be another measure of the torque constant. So I'm going to just sit there and step voltage. Every 0.1 volt, wait a half second, measure the resulting speed and plot it. Or in Thani, all that's the same, all that's the same. Same. Start at 0 volts. If the voltage is positive, put the PWM on pin, this pin, forward pin. Forward is pin 18, reverse pin 19. Apply the PWM on pin 18. If I want to go reverse, apply the PWM on pin 19. That sets the speed. Apply that voltage. 100% speed is 13.4 volts. That's my conversion from PWM volts to PWM. Apply that PWM, meaning that voltage, wait a half second, and then measure the speed of the motor, and print it, and save the data. So as I run that, here's what happens. So here on the screen, you can see this is the voltage. It's currently not spinning. Let's see, the second column is the speed in radians per second. As I get more and more voltage, it starts to spin. And it should be proportional. Ideally, speed is the torque constant times voltage. A little bit less because you have some IR losses. But ignoring the IR losses, that ought to be the torque constant. And current ought to be pretty low because there's no load. Power in equals power out. If there's no power out, no power in, there's voltage. For no power in, that means no current. Once you get this data, I can throw that into MATLAB. Or what I'm doing is take the data, saving it to an array, and then use the LCD graphics routine. So here's my setup. I've got the Pi Pico, my H bridge, the encoder, power and ground, go to 5 volts of ground. The two outputs go over here. The PWM outputs go to my H bridge. 15 volts, meaning 13.4 volts out, comes in as power. This goes to the motor. And after it collects all the data, it will plot the voltage versus speed. Should be just about done now. So here you can see the experimentally obtained voltage versus speed with the wire that's in the way. There's kind of a dead zone. It takes a little bit of voltage to get the motor to spin. And then the speed is basically proportional to voltage. If I take the data down here and plot it in MATLAB, that's what she looks like. If I look at the slope is 0.12 volts per radian per second. That's basically the experimental torque constant, off a little bit because it's actually the voltage is I times R plus KT times speed. I'm ignoring this term. But the current should be small because there's no load. There is a little bit of current because there's some losses in the motor. But that's basically the torque constant. Well, the slope is the torque constant. And a dead zone. It takes a little bit of voltage to get the motor to spin. Okay, so I'll start this. There we go. Take the step response. I apply 4 volts to it. It spins. Jump it up to 8 volts. Measure the speed versus time. And there she is. That's my experimental speed versus time for my step input. And notice that looks like a first-order differential equation. Well, in MATLAB, I can copy this data into MATLAB and plot it. That's what she looks like. I can then try to come up with a first-order differential equation that matches that step response. And I can do that as time goes from 0 to 2 seconds. Here's the transfer function. This is the DC gain for a 10-volt input. There's my time constant. Play around with the 5, play around with the 78 to get the 2 to match. And eventually get this. Matches up pretty well, meaning it's a pretty good model. What that gives me is this transfer function. The pole is that exponential, and the number on top sets the DC gain. So experimentally, this is basically the model for the DC motor. Kind of talked about that. So now that I have a model for the motor, let's do some feedback control. So this is kind of how the cruise control works on your car. I've got a motor, I've got a voltage. As I change the voltage, I change the speed. Instead of applying voltage, I want to set the speed. I want the motor to go at 30 radians per second. What the compensator does is it figures out what voltage I need to maintain that speed. That's the feedback control law, something covered in control systems. Well, I can figure out what K of S looks like. I can figure out what the closed loop system behaves like, doing some algebra. So the speed is G times K times the error. The error is reference minus speed. Doing some algebra, I get this as the transfer function. It's GK over 1 plus GK. Well, G, I know what that is. That is this guy. That's the gain of the motor. K is my compensator. That's free. I'm free as the design engineer to make that anything I want. A very common type of controller is called PID. This is simple because it's got 3 terms. People can adjust 3 terms pretty well. It works. So generally PID is actually a very common type of controller. The I term is an integrator. What it's doing is it's trying to search. There's some constant voltage I need to maintain the speed. Do a search to find out what that is. And what happens is I'm integrating the error. That's the difference in the two. If the speed is too low, the error is positive. Integrate a positive number, the voltage goes up. If I'm too fast, the error is negative, it comes down. And eventually I wind up with some voltage that maintains the speed. That's the integrator's job. Do a search to find the constant voltage to maintain the speed. The P term speeds it up a little bit. The D term speeds it up even more. So here we can just look at an I and a PI compensator. Let's start with an I compensator, meaning this is just an integrator. Suppose this is an integrator with a gain of K over S. What should K be? Well, here's the transfer function. Here's G, there's K, K constant over S. Multiply by S times S plus 5 to clear the denominator, and I get this as the transfer function. Now this part right here is all important. That's the poles of the closed loop system. Those poles tell me how the closed loop system will behave. Well, I can plot the roots to the system as K goes from 0 to infinity. When K equals 0, the roots are at 0 and minus 5. Let's get this out of the way. As K increases, the roots come together. I then start to get complex roots, and kind of by symmetry, this will go straight up and down. If I want to place the closed loop poles right here at the breakaway point, this has to be true. So analyze that equation at S equals minus 2.5, and I get K is 0.158. So this is the feedback control law, an integrator, the integrator gain, that puts my closed loop poles right here. And really what the locus tells you is if I is really small, this pole starts out really small and is really slow and sluggish. Crank up the gain, it gets faster and faster. Then I start getting complex poles, meaning overshoot in the step response. I can try that in Python. So here's my PI gains. P is 0, I is 0.158. For the first 5 seconds, my desired speed is 25 radians per second, then 50. I will then apply a voltage. It's P is 0, so ignore that term. 0.158 times the integral of the error. So here's the error, reference minus speed, integrate it, that's the integral of the error, I times that. If I apply that control law, I should get that response. Pull up 0.158. So let's try it. We'll go over to Thani, start this boy up. Initially my desired speed is 25 radians per second. Then it jumps up to 50. It records the data and then plots it. So there's my desired speed, actual speed. Zoom in on that. See a pretty clean step response. So that's my desired speed in blue, actual speed in red. That's kind of what I expect. I expect no overshoot, it's a real pole, and the settling time ought to be, I'll settle out as 4 over 2.5, or it's e to the minus 2.5t, the real part of the pole. If I take this data down here and plot that in MATLAB, I get this. So there's my desired speed, actual speed, desired speed, actual speed. That's response of an integrator. And the transient, this guy right here, should be decaying as t e to the minus 2.5t. I have repeated poles at minus 2.5, gives you this transient response. To find out how long it takes to get to 2%, I just do 0.02 as t e to the minus 2.5t, solve. Should take 1.8 seconds. And here's 5, 6, there's about 1.8 seconds. Looks about right. So the motor's behaving like I expect. And the corresponding code. That's a P controller. Well, I could do even better, do a PI controller. With the PI controller, I've got two terms, a proportional and an integral term. Doing some algebra, put this over a common denominator, factor out the P, and what this looks like is I've got a gain K, I've got a 0 I can place anywhere I want, and an integrator. The integrator is good. What I'm trying to do is find out what voltage holds the speed. That's a constant. Integrators are really good at estimating constants. But I've got a 0 I can put anywhere I want. Well, what that 0 does is, here's the dynamics of my plant, I can make these two cancel. So put the 0 on top of the pole, and what I wind up with is this as the open loop system, G times K. Close the feedback loop, and I wind up with that transfer function. If I plot the roots to the denominator, that gives you a thing called the root locus plot, something that we cover in control systems. But that's actually pretty simple. It's S plus 39.5k equals 0. So the root starts at 0 and just goes left. And the root location is 39.5k. If I want a very specific response, like I want the pole to be at minus 10, then k is 0.253. So there's k of s, 0.253, s plus 5 over s. And that should give me this closed loop system. That's my PI compensator. This is equal to P plus I over S, or it's equal to P times S plus I over P over S. So P is 0.235, I is 5 times P. Let's try that. So P is 0.235, I is 5 times P. Let this puppy run. So just change those two gains and let her rip. So here's the desired speed is 25. Now 50. Record the data and plot it. Zoom in and you can see the response is actually quite good. I tell it to go 25 radians per second, and it is. Tell it to jump up to 50 radians per second, and it gets there very quickly. This is the transient that decays as e to the minus 10t, because that's where I put the closed loop poles. I can also take this data, copy it and plot it in MATLAB, and that's what she looks like. Actually looks better the last run. That's your PI controller. And this is something that's covered in control systems. But with the Raspberry Pi Pico, I have a way to measure motor speed. I have a way to implement my controllers. I can do different types of feedback. Now what I'm doing currently is I'm doing this in the main routine. So here's my main loop, always running. This is kind of a problem because the main loop is now tied up with the feedback controller. I might want to use the microcontroller for something else. Well, you can do that. If I use interrupts, I've got the interrupts running for time every 20 milliseconds. I could implement this voltage control law inside the interrupt. If I did that, then the main routine would be free to do whatever you want. One kind of sidelight, there's a thing called inrush current with motors. On this motor, this is a small enough motor, I don't have to worry about it, but the larger motors you do. A problem with motors, this is the voltage going into the motor. This is I times R losses, inductance, KT omega. Well, the current in the motor is your voltage minus back EMF over resistance plus LAS. This is pretty much small, so kind of ignore it. When the motor spins, the back EMF limits the current. On startup, however, omega 0, so this term's not there, I can get a really large current on startup. That's called inrush current. That inrush current can burn out your motor. And what that looks like is if I apply a step input, here's the speed of the motor. Initially the speed is 0, so we got a large current. As the speed goes up, the back EMF increases by KT omega, the torque constant. That helps to limit the current. I'm always left with a little bit of current. That takes up the losses in the motor. But this inrush current can be huge, and oftentimes motors are not designed to handle that much current. Essentially, my motor is going to be operating over here most of the time. The only time I get this much current is on startup, and I only get that when I apply a step input. So to save money, oftentimes motors are not designed to handle that much current. So what you can do is, if it's a small motor, not worry about it. The motor I have is 26 ohms, 13.4 volts. The most the current is going to be is 500 milliamps. The motor can handle that. If you take a larger motor, like this Allen Bradley motor, it's a 90 volt motor, 0.6 ohms armature current. That's 135 amps. The maximum armature rating is only 5 amps. This is way above that. Apply a 90 volt step, you're going to burn out the motor. You can get around that. Instead of applying a step input, I'll do a slew rate limit. I won't apply suddenly 90 volts to the motor. I'm going to ramp up to 90 volts. Kind of like that, called a slew rate limit. That's one way to reduce the inrush current. Give the motor a chance. Let it speed up. Just kind of a sidelight. But with that, we can now control the speed of a motor, and it's actually working really, really well. So that is lecture number 18 for ECE476. Once you have edge interrupts and timer interrupts, you can measure and control the speed of a DC motor, and it's not that hard. PWM signal works really well with H-bridges. That allows you to control the motor speed from 0 to 100%. Edge interrupts, along with an optical encoder, let you measure the motor speed as pulses per second. The timer interrupt lets you set the sampling rate needed for numerical integration. And an I and PI controllers can then be implemented by using just a couple of multiplications and additions. The result is a motor which can track a constant set point dead on, or a time-varying set point fairly well, as long as the set point doesn't change too fast. For example, this should have a bandwidth out to 10 radians per second. If I apply a 1 radian per second sine wave, the motor will speed up, slow down, follow the reference. And what you get is the reference is the blue line, the actual speed is red line. I've got a glitch in my sensor. It's tracking pretty well at 1 radian per second. Change that to 5 radians per second. It should still mostly work. tracking pretty well. Go too much faster, and the bandwidth is only 10 radians per second. It'll have a hard time tracking eventually. Let's see. So again, with what we have right now, we can now control the speed of a DC servo motor. That's lecture number 18 for ECE476.